In this video, you will learn about specific heat, which is given as C, of a substance, then the heat or enthalpy of solution or heat and enthalpy of neutralization, and how to calculate these quantities using experimental data that is plugged into the formula given below. So, specific heat of a substance is the quantity of heat required to raise the temperature of a unit mass of a substance by 1 degree Celsius, and it is measured in joules. The unit mass could either be grams or kilograms. So say there is 1 gram or kilogram of water and a piece of aluminum. Initial temperature of both substances is 20 degrees Celsius. The specific heat C is the quantity of heat required to increase the temperature by 1 degree Celsius, that is, to 21 degrees Celsius. So initial temperature is T1, final temperature is T2. Delta T is the difference in the temperature, and in this case it is 1 degree Celsius. The specific heat for water is a standard value of 4.18 joules per Kelvin per gram, and 4.18 times 1000 joules per Kelvin per kilogram. For aluminum, it is 0.902 joules per Kelvin per gram and 902 joules per Kelvin per kilogram. So, when heat flows into a substance, the change in temperature, which is given as delta T, depends on the nature of the substance. That is, the specific heat of that substance. And for every substance, there's a separate standard specific heat. It also depends on the mass of the substance. We are not always working with 1 gram or 1 kilogram. And the quantity of heat, Q, flowing into the substance. So if there is a piece of aluminum and Q is the quantity of heat flowing into aluminum and heating it up, which has a mass M, and the specific heat is given, which is a standard value, then the change in temperature, delta T, can be calculated using the formula Q is equal to M times C times delta T. Plug in the values of Q, M, and C and calculate delta T. Here you have to be careful whether the mass is in kilograms or grams, and you have to match the specific heat with the units of the mass. So if mass is in grams, then use specific heat with units joules per Kelvin per gram. And if mass is in kilograms, then use specific heat with units joules per Kelvin per kilogram. Also, units for temperature, T1 and T2, that is the initial and final temperatures, are measured in degrees Celsius using a thermometer. Change in temperature is the difference in temperature, so you can use Kelvin or degrees Celsius in the units of specific heat. So whether the specific heat of water is 4.18 joules per Kelvin per gram or joules per degrees Celsius per gram, it doesn't matter. So here's an example where a piece of zinc is heated and its temperature is raised from 16 degrees to 66.3 degrees Celsius, and then it's placed into an insulated cup containing water. And the heat flows from the zinc into water, and you have to calculate the final temperature of water. So the first thing is to note down what is required and what is given. Required is the final temperature of water, T2, and given is the mass of zinc, the specific heat of zinc, the initial temperature and final temperature of zinc. Mass of water can be taken as 50 grams, where 50 milliliters would be equal to 50 grams because density is 1 gram per milliliter. And then the specific heat and initial temperature of water is given. So the first thing you would do is to calculate the quantity of heat flowing into zinc. So you have the mass in 12 grams, calculate delta T. Specific heat is given, and note that the unit for specific heat has grams. So we leave the mass of zinc as 12 grams and you don't need to convert it into kilograms. And you put in the values and calculate the specific heat, which is 230.6 joules. Next, you put the piece of zinc into water and assume that all the heat Q flows into water and there's no heat lost to the surrounding. The mass of water is 50 grams. Initial temperature is 27 degrees Celsius. And there would be a change in temperature as the heat flows into water, and we calculate delta T, and from that we calculate the final temperature T2. Specific heat of water has the units with kilograms, so it's important to convert the mass of water also into kilograms. And we already have the value of Q. We plug in the values and calculate for delta T, which is 1.1 degrees Celsius. And lastly, we can calculate the final temperature T2 by adding up delta T with T1. And the answer is 28.1 degrees Celsius. Molar heats of solution and neutralization can also be calculated by a similar method. Molar heat of solution is defined as the heat absorbed or released when 1 mole of a substance completely dissolves in water. Note that the mass of the substance dissolved, m, must be converted into moles because that is the definition of heat of solution or enthalpy of solution. It's always per mole. So if you have sodium hydroxide dissolving in water, you can calculate the enthalpy of dissolution. So if you have, say, 4 grams of sodium hydroxide and you dissolve it in 200 grams of water or 0.2 kilograms of water, sodium hydroxide dissolves and dissociates into sodium ions and hydroxide ions. So there will be some energy changes and therefore there will be a change in temperature. Initial temperature, if it is 19 degrees Celsius, final is 24.3. Delta T can be calculated. Note that the specific heat, it's given in kilograms. Therefore, it's important that the mass of water should be also converted into kilograms, and put in the values of mass, C, and delta T and calculate Q. The next thing you would do is calculate the amount in moles of sodium hydroxide that was dissolved in water and divide the mass by molar mass, and you would get 0.1 moles. And lastly, the enthalpy of dissolution can be calculated by dividing Q by N, and you would get the value in joules per mole or kilojoules per mole if you divide it by 1,000. Note that the temperature of water increased when sodium hydroxide was dissolved in it, so we can infer that it's an exothermic process. So it's important that you report the answer with a negative sign. So enthalpy of dissolution would be minus 44.308. Remember that Q is simply the flow of heat from a hotter to a cooler substance, so it does not have a positive or negative sign, but enthalpies or heats of solution can be exothermic or endothermic, and it's reported with a positive or negative sign. Heat of neutralization is the heat released when 1 mole of either an acid or a base is completely neutralized. Hydrochloric acid reacts with sodium hydroxide to form sodium chloride and water, and we can calculate the enthalpy of neutralization. The first step would be to determine the limiting reagent. So you calculate the amount in moles of hydrochloric acid and sodium hydroxide using the concentration and volumes given. And from this, you can see that hydrochloric acid is the limiting reagent, and therefore it will determine the heat released when both solutions are mixed in an insulated cup. So once you mix the two solutions, you determine the quantity of heat released. M would be the total mass of the solution when acid and base are mixed. C would be the specific heat of water because it's an aqueous solution, and change in temperature can be measured. And lastly, heat of neutralization would be again Q divided by N, where N is the amount in moles of the limiting reagent. So the workbook has questions on specific heat, heat of solution, and neutralization. So good luck and enjoy.